everyone. Today we are going to study based on the adsorption process. If you recall, in our previous lecture we have discussed about the adsorption process, the concept, the mechanism behind the adsorption of the adsorbate onto the surface of adsorbent. Then we have discussed also the various isotherm, the mass balance analysis. So now how these adsorption isotherms they are developed, for that there are various studies to be performed. So in this lecture we will be dealing with the batch study which is carried out for development of isotherm. Then we will be also discussing about the column study which is used to carry out the breakthrough analysis and to design a adsorption column. So there are various design parameters. So all those design parameters we will be taking one by one in this lecture. So let us discuss about the batch study, why this study is performed. Basically, as we have discussed, there are various isotherms to develop, to determine the various parameters of different isotherm. We have to conduct this batch study. So this batch study is performed by taking a fixed amount of samples, say 100 to 250 ml in different volumetrical flasks. Say we have taken 4 to 5 number of flasks, and then we have to add different amounts of adsorbent starting from say 0.5 gram, 0.6 gram, 0.7 gram, like that different doses of the adsorbent in all these flasks. And then after adding the adsorbent into the solution and mix thoroughly in a rotary shakers till the equilibrium is achieved. So equilibrium is basically when the further adsorption does not occur. So that condition we say that is equilibrium conditions, and this depends upon the type of adsorbent we are using. After this equilibrium is achieved, then the samples has to be filtered, and after filtration this samples has to be taken out from each flask, and then it has to be analyzed for that pollutant. So we will be having here the initial concentration, say C0, and then after analysis, say if the concentration becomes CE, that is after the equilibrium. So this concentration and the different doses of the adsorbent which is added into the different flasks, that we have to note down, and then we can analyze the various isotherm and their model parameters. So here if we see, this is the procedure whatever I have explained. So we have to take a definite amount of samples, say 100 to 50 ml in each flask, and then we have to add different doses of adsorbent into different flask, and then it has to be mixed in a shakers, and after the equilibrium or minimum time allowed for samples to achieve the equilibrium, that is normally 7 days for powder activated carbon. However, this varies from type of the adsorbent. So at the end of this test period, when equilibrium is achieved, we have to take out the samples, it has to be filtered, and then the amount of adsorbent which is remaining in the solution, that has to be measured, and the analysis is performed to find out the different isotherm parameters. So how to find out these isotherm parameters? For that we have to plot the isotherm. So here if we see the Langmuir isotherm, as in the previous lecture we have seen this Langmuir isotherm, the linearized form of this isotherm we can write as 1 by QE, that is equal to 1 by Ka into Qm multiplied by 1 by Ce plus 1 upon Qm, where this QE is basically the adsorption capacity at different equilibrium time, and then this Ka is basically the Langmuir isotherm constant, and then Qm is basically the maximum adsorption capacity, whereas Ce concentration of adsorbate remaining after the equilibrium is achieved. In this equation if we see, this is like Y, this is like M, and this if we take as X, so we will get Y is equal to Mx, and this if we take as C, so this we will have a straight line plot So in the form of y is equal to mx plus c. So here you can see this slope is 1 upon k into qm, whereas the intercept we can get by plotting the isotherm curve. So this, if we plot 1 upon qe onto the y-axis and 1 upon ce onto the x-axis as per the isotherm model, its linearized form, then we will get a straight line. And this straight line, if we find out the intercept and if we find out the slope of this straight line, we can calculate these model parameters. So here in this, if we see this 1 upon qe, this is the equation of the isotherm, and in this the intercept, that is 0.01123. So this 0.01123, that will be equal to 1 upon q max. So 1 upon q max, that will be equal to 0.01123, and the slope, that will be equal to 1 upon ka into q max, that will be equal to 0.44. By using this, if we know this 1 by q max is equal to this, so we can find out q max value, and similarly in this equation, if we put that q max value which is obtained from this relation, so we will get the value of Langmuir constant k. So this is how we can find out the model parameters by using batch study. The column study is also performed. So this column study is performed to find out the design parameter of column. So this study is done in a continuous mode, whereas the batch study, it's in a batch mode. So here what we have to take, we have to take the wastewater sample which having certain pollutant having concentration C0, so which is taken as a adsorbate concentration, and from this, if we see, this tank is connected with the pipeline and one control valve is fitted here so as to control the flow of the wastewater through this pipeline, and then this wastewater is allowed to fall into this funnel which is attached with the adsorption column, and this column, if we see, this is the packing of the adsorbent, say activated carbon, so this will be packed within the column and the water will be allowed to percolate through this column, and from the bottom of this the samples will be collected at different point of time, at different interval of time, and it will be analyzed for its concentration. So we will have initial concentration which is there in this tank, and the final concentration at different time interval, say at time t, say this is equal to c, and then we have to plot the breakthrough curve and we can analyze different model parameters. So here, how to plot this breakthrough curve, how to find out the point of breakthrough and the point of exhaustion. So this is done by plotting the breakthrough curve, and you can see here this is the normalized concentration, this is C by C0. It means the ratio of the concentration of the adsorbate at any point of time with respect to the initial concentration of adsorbate in the solution. So this normalized concentration is plotted for different time interval, say T1, T2, T3, till the bed is exhausted. So here if we see the breakthrough curve we have got for adsorption study. So here how to find out this breakthrough point, how to find out the point of exhaustion. Basically breakthrough point is defined as the point when the concentration of the adsorbate in the effluent comes to around 5% of the initial concentration of adsorbate in the solution. So C by C0, that must be equal to 0.05. So corresponding to C by C0, we have to draw a horizontal line and then we have to draw a vertical line where it intersects. That will be called as the breakthrough time. Whereas concentration of the adsorbate in the wastewater will be termed as the breakthrough concentration, and that is equal to C by C0 equal to 0.05. Then if we further analyze this breakthrough, we will get that the 50% of bed is exhausted at C by C0 equal to 0.5. So there again we can draw a horizontal and vertical line, and then we can find out what is the 50% adsorption occurring at that particular time. So this time indicates that time at which the 50% of the capacity of your adsorption column will be exhausted. Similarly, there is another point of concern, that is point of exhaustion. So this point of exhaustion at C by C0 equal to 0.9 to 0.95. We should take this as a point of exhaustion, and when the C by C0 equals to 1, it means the concentration of the adsorbate that is coming after the adsorption, that is equal to the initial concentration of adsorbate. Then this point is called as the complete exhaustion of the bed, and this is defined as the time of complete exhaustion, that is TE. So here this breakthrough study is carried out not only to find out the breakthrough time, but it is also carried out to analyze the type of adsorbate, its nature, what type of adsorption is occurring. So another important aspect in breakthrough study, that is mass transfer zone. Mass transfer zone, basically this is the length of the adsorbent bed where the adsorption is occurring. Basically this we determine by using this equation, which is equal to HMTZ, where this HMTZ indicates the height of the mass transfer zone or the length of the mass transfer zone, which will be equal to Z, where Z is the height of the adsorption column, and then in bracket there is a VE minus VB. So BE and VB, they are basically the throughput volume of the water at the point of exhaustion and at the point of breakthrough respectively. And using these two parameters, we can define what is the height of the mass transfer zone. And if we see here the mass transfer zone, basically this depends upon the hydraulic loading rate. If the hydraulic loading rate is very high in the extreme conditions, then the height of the mass transfer zone may be even greater than the height of the adsorption column, which means that the adsorbate will not be further removed, and the calculation of mass transfer zone is very important to define the height of the column. If we further analyze the breakthrough curve, so here if we see, this is the throughput volume of the water at the point of breakthrough, and this is at the point of exhaustion, and here this, if we see, this is normalized concentration. In the beginning, if this is the height of the mass transfer zone, so column has sufficient height where this adsorption process can occur, but as soon as the adsorption proceeds, the adsorbent beds getting exhausted and height increases, and finally the condition arises when the depth of the column is even lesser than the depth of the mass transfer zone. So in this condition, you see there won't be any adsorption, and this is basically the point of exhaustion of the bed when the C by C0 that is equal to 1. So this height of mass transfer zone is very important to finalize the overall height of the column required for this adsorption process. By analyzing the breakthrough curve, we can also determine a very important characteristic of the adsorbate which is present into the wastewater. So here if we see, there are 1, 2, 3, 4 different types of breakthrough curve, and in these two cases, if we see this C by C0, that becomes equal to 0 for these two curve. So it means whatever the adsorbate that is present, it is completely adsorbable nature. So it will be 100% absorbed. If we analyze its end point, one is finished at a point C by C0 lesser than 1, and this curve is the C by C0 that is equal to 1. So if the C by C0 is less than 1, what does it mean? That the adsorbate concentration is not coming out even after the exhaustion of the bed. It means something is being degraded within the adsorption column. So this type of curve indicates basically that the adsorbate is also biodegradable or degradable. Within the column, some of the adsorbate is being degraded. That's why this C by C0 is not coming equal to 1. While if the C by C0 in this case, if it is equal to 1, it means that is non-biodegradable. Means whatever is coming into the column, the same is coming out of the column. It means the adsorbate that is non-biodegradable. So the nature of the breakthrough curve, we can find out the nature of the adsorbate present into the wastewater. So in these two graphs, if we see the C by C0, initially it is more than 0. So if it is more than 0, it means there are certain, the adsorbate is not completely adsorbable. So some part is adsorbable, some part is not adsorbable. That's why in the beginning itself there is no complete adsorption and the C by C0 is more than 1. So this type of curve indicates that the type of adsorbate which is adsorbable also, not adsorbable also. So this is the different aspects of breakthrough. So finally, using this breakthrough, we find out the breakthrough adsorption capacity, which is basically 25 to 50% of the theoretical adsorption capacity, and this can be determined by using this formula where X by M B, that indicates basically the breakthrough adsorption capacity, which is equal to XB divided by mass of granular activated carbon MgAc. So XB indicates the amount of adsorbate being adsorbed till the breakthrough, whereas this MgAc that gives the amount of granular activated carbon. So the ratio of the two basically gives you the breakthrough adsorption capacity, which is equal to Q into C0 minus Cb by 2 into Tb divided by mass of granular activated carbon, that is MgAc. So whereas in this, if we see, the Q is basically the flow rate, that could be in meter cube per day, that could be in liter per day, whereas C0, that is the initial concentration of adsorbate present in the solution, while Cb is the concentration of adsorbate at the time of breakthrough. So average of the two, C0 minus Cb divided by 2, that has to be taken, and then it has to be multiplied with the time of breakthrough, and then by using this equation we can find out what is the breakthrough adsorption capacity. Then let us design a granular activated carbon. So again we have to perform the mass balance analysis. So if we see, this is a column. So in this column adsorbent is filled and the wastewater enters here at a flow rate of Q having initial concentration C0, and here this is the same flow will come out, and here we have taken that granular activated carbon. So if this is condition, and say after time t the concentration becomes C. So for this, how to perform the mass balance analysis and then to find out different design parameter of granular activated carbon. So here if we see, this is the mass balance equation, that is the basic equation, accumulation is equal to the inflow minus outflow minus amount being adsorbed. In this case the accumulation is 0 and the inflow, that is Q0 into C0 into T, means how much amount of adsorbate is getting into the column. This is Q into C into T. This gives how much the adsorbate going out of the column, and then this is how much adsorbate being adsorbed within the adsorbent, that is MgAc into QE. So if we further solve this equation, what we will get, that is m GAC divided by QT. This will be equal to C0 minus CE divided by QE, which is defined as the adsorbent usage rate. So adsorbent usage rate is basically defined as the amount of adsorbent being used per unit volume of wastewater. So this is equal to C0 minus CE divided by QE. CE is equal to 0. If we presume that the concentration after the equilibrium becomes very negligible, then this adsorbent usage rate means m GAC divided by QT, that can be written as C0 divided by QE. So this equation we can also use when we neglect the concentration of adsorbate in the solution after the equilibrium. So these are the two equations we use to determine the adsorbent usage rate. Similarly, another parameter which is called as the empty bed contact time. Empty bed contact time is the time for which the adsorbate remain in contact with the adsorbent. So this is determined by the volume of the adsorbent bed divided by the flow rate. So this volume of the bed, if we further write in terms of its area and depth, so this will be equal to area of the bed into depth of the bed divided by this. The flow rate, if we write in terms of velocity of flow, then this will be equal to velocity of flow into area of bed. So area of bed in the denominator and numerator, that will get cancelled, and we will have this depth of the bed divided by velocity of flow through the bed. Then another important parameter that we use to determine the total amount of activated carbon required, that is activated carbon density. As we know, this is the ratio of the mass to the volume. So this is mass of the granular activated carbon filled into the column having its bed volume equal to BB. So by taking the ratio of the two, we can find out the density of the activated carbon. Then we have specific throughput volume of water treated. So this specific throughput, that is defined as the volume of water treated by per gram of the adsorbent used. So this is defined as the specific throughput volume, which the unit is in meter cube per gram, and this can be determined by this equation, that is equal to Q into T divided by mass of granular activated carbon, that is mGAC, where Q and T is defined as earlier. And here if we Q again put in terms of volume of bed, so this will be volume of the bed divided by EBCT, that will give you the value of Q, and then this is T and divided by mass of granular activated carbon, so mGAC. So any of the two equations we can use to find out the specific throughput volume, which is basically the amount of volume of water that is being treated per unit volume of adsorbent. Then similarly, we have another form of this. We can write this VB into T divided by EBCT. Then this mass of this granular activated carbon, we can replace it by density into volume of the bed. So density of granular activated carbon into this BB will give you the mass of granular activated carbon. So after substituting this value, we get finally the specific throughput volume we can calculate using this another equation, that is equation number 7. And then similarly the carbon usage rate. So carbon usage rate, that is basically how much carbon is required for treating unit volume of the water or the wastewater. So this is a CUR, which indicates the carbon usage rate, and its unit, that is in gram per meter cube. If we write, this is mass of granular activated carbon divided by Q into T, which is basically the volume of the water. So this will give you the carbon usage rate, and this, if we see, this is the inverse of the specific throughput volume. And then similarly the volume of water treated for a given EBCT time, that if we have to calculate, so this will be equal to mass of granular activated carbon divided by GAC usage rate. So this will give you how much volume of the water can be treated by having a particular EBCT time. And then similarly we can calculate the bed life. So this is basically the total amount of water treated for a given EBCT divided by the flow rate. If we do, we can find out the overall bed life of the activated carbon. So again, if we see the major aspects of design of the granular activated carbon, so we see that is contact time, hydraulic loading rate, then depth of the activated carbon, and then how many number of units we have to design. So a minimum of 2 parallel carbon contactor unit is designed, but in case of there are multiple units, so one unit we can keep it as a standby and then rest of the unit will keep on working. So as some of the units they require regeneration, so one standby unit is always preferred for this granular activated carbon. And then this is the type of example which we have to find out Langmuir and Friendlich isotherm coefficients using the test data which is given below. So this is basically the mass of the granular activated carbon added. So this is 0.00 means nothing is added. Here 0.01 gram is added, then 0.01 gram is added. So for different doses of this granular activated carbon, there is a CE value is given 3.37, 3.27. So like for different doses of this, the CE value is given, whereas the initial concentration of this adsorbate in the solution is given as 3.37. So equilibrium time is obtained after 7 days. So this is calculation table. You can see C0 value is given and here CE value is given. So from this we can calculate C0 minus CE, and then this is the mass of the adsorbent added. So this is QE value we get, that is milligram of adsorbate being adsorbed per gram of adsorbent. So this CO minus CE divided by doses of adsorbent being added. So this has to be divided, so we will get this data. So we have to also calculate this CE by QE value. So CE value is given here, QE value we calculated here. So find out this CE by QE in another column. Similarly, in this case also, as per the calculation, we have to find out the plot for Friendlich isotherm, then plot for Langmuir isotherm. So if we see, this is the equation of the straight line plot of Friendlich isotherm. This is the equation for straight line plot of Langmuir isotherm. So here if we compare the R square value of this, both of these two models, so we see the R square value of this Langmuir model is much better than this R square value of Friendlich equation. But here if we find out the slope, that is 1 by Q max, the value comes here, this is negative, because the trend line if we see that is going downwards, so does not meet with the fundamental assumption of Langmuir isotherm, and this Q max value cannot be negative. Because of this, though the R square value of this plot is much higher compared to this R square value of Langmuir model, but it will not comply with the adsorption process, because the Q max value here what we get from this plot is negative, which is not at all possible. So we can conclude that this isotherm does not comply with the adsorption process. So in this we see this is the Friendlich isotherm model, which implies slope equal to 5.0767, which is equal to 1 by n. So from this we can find out the value of n, and similarly the intercept, that is minus 0.8344. So if we put equal to Kf, so Kf value also we can determine equal to 0.1464. So this is how we can determine the model parameter using different isotherm data. And then this is another numerical which deals with the fixed bed column study. So here if we read this, a fixed bed activated carbon absorber has a fast mass transfer rate, and the mass transfer zone is essentially a sharp wavefront. Assuming the following data applied, determine the quantity of carbon required to treat 1000 liter per minute of flow, and also find out its bed life. The given data is this, like compound is TCE, that is trichloroethylene, initial concentration that is 1 milligram per liter, and its final concentration after the equilibrium that is 0.005 milligram per liter. Similarly, the other data for density of the granular activated carbon is given, which is equal to 450 milligram per liter. And then the model parameters like Kf is given. So this is Friend-Village capacity factor. So Kf value is given, and also its intensity parameter 1 by n is given equal to 0.62. And then EBCT time is given equal to 10 minutes. So here from the problem we can see this follows the Friend-Village isotherm model, and the initial concentration and final equilibrium concentration is given. So for this we have to find out how much dose of carbon is required and what will be the bed life of the column. So first of all we have to find out the GAC usage rate for this TCE. So this GAC usage rate, that is mass of the granular activated carbon divided by Q into T. So this will be equal to CO minus CE divided by QE. And again if we QE we write equal to its Kf into CE raised to the power 1 by n, because it follows the Friend-Village isotherm. So we can write is as QE equal to Kf CE raised to the power 1 by n. And now if we put the value of CO minus CE, so that is 1 milligram. Equilibrium concentration is very less, so we can neglect this concentration. So C minus C will be equal to C0, that is 1 milligram per liter. And then this is the Kf value, that is given as 28. And then this is CE value, which is given as 0.005 to the power of 1 by n. So 1 by n is also given, that is 0.62. So if we put this value in this equation, we can find out what is the carbon usage rate, that is 0.953 gram of granular activated carbon is required for treating 1 liter of flow. Then we can find out the mass of the carbon required for a given EBCT time. So EBCT time here, if we note, that is 10-minute time. So for 10-minute time, how much mass of GAC will be there in the bed? So this is volume of the bed into density of the granular activated carbon. So this is equal to EBCT into Q into density of the granular activated carbon as defined earlier. So by putting the value here, we can find out how much activated carbon dose is required. So here EBCT time, that is 10 minutes, then Q is 1000 liter per minute, and then this is density of the granular activated carbon, which is equal to 450 gram per liter. So after calculating, we will get this much dose of granular activated carbon is required. And then here if we see, this is the volume of the water. How much volume of the water we can find, we can treat within this 10-minute EBCT time. So this will be equal to mass of the GAC added into the adsorption column for a given EBCT time and divided by the GAC usage rate. So GAC usage rate already we have calculated, that is 0.953, and this is the amount of adsorbent that we are using, we have calculated, which is equal to 4.5 into 10 raised to the power 6. So if we divide these two, we get this value, that is equal to 4.72 into 10 raised to the power 6 liter, or we can say this is 4.72 million liter. Then similarly we can find out how much bed life will be there for the column. So this is bed life, which is equal to the volume of the water being treated divided by its flow rate. So this is the total volume of the water, which we have got 4.72 million liter. So 4.72 into 10 raised to the power 6 divided by its Q, which is the flow rate. So this is 1000 liter per minute. So if minute we convert into day, so this will be multiplied by 1440. So by converting it into day, we get this is the overall bed life for that activated carbon. So this numerical discuss about the application of those concepts in determining the adsorbent dose, determining the bed life. Then this is another example. If we read, this is a treated wastewater with a flow rate of 1000 liters. The flow rate is given as 1000 liter per minute is to be treated with the PAC to reduce the concentration of residual organics measured as TOC from 5 to 1 milligram per liter. So initial concentration is 5, 1 milligram per liter is the equilibrium concentration. And then what it says that French adsorption isotherm parameters were developed as discussed previously. Assuming the following data applied, determine the PAC requirement. Again the same thing. To treat the wastewater flow is already given, that is 1000 liter per minute. Assuming the following data, the data is given. So this is mixed of organics. C0 is 5 milligram per liter, CE is 1 milligram per liter, GAC is 450 gram per liter, KF is 150, 1 by N is 0.5. So we can see quickly. So this is PAC dose. Using following equation we can determine. So this is M by V is equal to C0 minus C by QE. QE if we put equal to KFC, so in the equation form, so CO minus C will be equal to Kf into C raised to the power 1 by N. So this by this we can get M by V value. So this M by V value came by putting the value CO minus C, then this is Kf, then this is C, and this is 1 by N. So after putting this value, we get the value of PAC doses, that is equal to 0.0267 gram per liter. And then the annual cost we can calculate for a given flow. So this is 0.0267 multiplied by the flow rate. The flow rate to be converted in per day. So 1440 is again multiplied. Then for a year 365 is again multiplied. And then this is the cost of the per gram per kg of this adsorbent. So this is in gram. So we have to convert into per kg so that per kg cost can be multiplied. And then finally we get the total annual cost for this adsorption process. That is $7,008 per year. So these are the references we have followed. Thank you.